Good afternoon, folks. How are you today? We just learned in our last class how to solve a second order differential equation. And we did that by converting a second order differential equation into two first order ordinary differential equations. And we did this all just by substituting one variable for another. So remember, we were given a second derivative of y with respect to x was a function of x, y, and y prime. So all we did was we said we are going to define a new variable z, which is same as y prime. So this differential equation then becomes dz dx is a function of x, y, z. So since now we have two new variables, two dependent variables, we need a second differential equation, which is what we did by this variable substitution. And we can use then any method to solve a system of first order ODEs. So when we have a initial value problem, we could use Euler's method, which we did last week, and we could use Runge-Kutta method, which we did in last lecture. So our last topic is going to be how to solve a second order boundary value problem. So remember, what we did was we solved here a initial value problem. What we mean by that? We knew that z at x0, which is same as y prime at x0, y0 prime was given to us. And of course, y at x0, which is y0, was also given to us. So we were given both y and z at same x value. So that is what is called initial value problem. Now, if instead, if we look at second order ODE, but boundary value problem, that says that if we have a second order differential equation, we might be given y and y prime at different locations. And there are various combinations we can also have. So these kind of boundary conditions are called Dirichlet or Neumann boundary conditions. So what we are going to do is we are going to convert the boundary value problem now into an initial value problem by making a guess about whatever condition, initial condition we are not given at x is equal to a, and then match the known boundary condition that we are given at x is equal to b. So let's see what kind of combinations we can have. So let's suppose we are given one boundary condition at x is equal to a and another boundary condition at x is equal to b. So we could have four combinations. We could be given y at both locations. We could be given y prime at a, but y at b. We could be given y at, let's see, y at a, but y prime at b. Or we could be given both y prime a and y prime b, four combinations. So what we do is Whatever we don't know at A, we use as a guess. So we guess the other initial condition at x is equal to A. So if we are given YA, we are going to guess Y prime A. If we are given Y prime A, we will guess YA. We'll guess here Y prime A. We are given Y prime, so we will guess YA. So now we will have our initial conditions. So we have converted our boundary value problem into a initial value problem that we can solve. And then this becomes our match parameter. Match this boundary condition. So we will then need to see how we can generate a series of better and better guesses. So that would be our problem. And that is what is called shooting method. So it's like a trial and error method. And let's do it by doing an example. So we'll pick up our old second order differential equation where we are given that y double prime is, which is a function of x, y prime, is x minus y plus y prime. And we are given that at x is equal to 0, y is equal to 1. And our other boundary condition is at x is equal to 1, y is 1.5. Since we are given y, what we are going to do is we are going to guess at x is equal to 0 what is y prime. And then we are going to match this boundary condition. Okay. So we are going to solve our initial value problem by Euler's method, since we are going to do it manually. So in Euler's method, we know y prime I plus 1 is yi plus h times y prime I. Right? Sorry, this is yi. Y prime I plus 1 is y prime I plus h times the function. Now our function is x minus y plus y prime, so let's just write it, x minus y plus y prime. Okay, and we are going to use h is equal to 0.25. Okay, so let's start our first guess. Let's say y prime at x is equal to 0 is 0.5. So we solve xi, yi prime. At x is equal to 0, y is 1, guess is 0.5. Remember, this was not given to us. So we will solve for x 0.25, 0.5, 0.75, and 1. Now you may remember you solved exactly this initial value problem in the last lecture. And I'd asked you to calculate along with me. I had done the first two rows. So we got 1.125 over here, 0.3750 here. We got 1.2188 and 0.25. Right? Let's do one more, 1.2813. Remember, we are just using these two equations. And then we get 0.1328, 1.3145, and 0.0332. So by making this initial guess, we get our target to be 1.3145. So obviously our slope, so think of the slope as a gun that we are shooting. Okay, so think of this. This is x, this is y. At x is equal to 0, y is 1. At x is equal to 1, this is our target. This is what we want to shoot, 1.5. So we put our rifle at a slope of 0.5. So our bullet traveled and it hit 1.3145. So now what we want to do is we want to raise our slope. So let's make our second guess. Y prime at x is equal to 0, let's say, is 1. So let's make our table again. Xi, yi, y prime I, 0, 1, 1. So this is our guess, remember. Again, we solve our differential equation, initial value problem. So we get 1.2500. This is 1. We get 1.5000. This remains 1. 1.7500 remains 1. 2.00 remains 1. So now we wanted to get 1.5, but instead we shot at 2. So if you go back to our previous page, we had put our gun now at slope of 1, and this time we hit high. We hit at 2. We wanted 1.5, but we hit at 2. So now the question is, how should we get our third guess? So let's summarize. So when we had a guess of 0.5, we hit our target at 1.3145. Then we use 1.0, we hit 2.00, and we want to hit at 1.5. That's our goal. So what we can do is think of it graphically now. This is our guess T. That's our guess, and this is our target T. So obviously they have some kind of a relationship. We want our target to be 1.5 here. Let's call this target to be T ideal or T wanted. So what we did is when we made a guess 1, we hit our target 1. When we did guess 2, we overshot, we hit target T2. We want T ideal. So what we can do is we can connect these both with a straight line. And we can say this can be our next guess, G3. So what we are doing is we are using secant method. We are doing extrapolation to get our next guess. Okay, so let's derive our equation. So let's say this is angle theta and this is angle theta. So tangent of theta using big triangle is T2 minus T1 over G2 minus G1. If you use small triangle, T2 minus TW over G2 minus G3. Okay, so we want to get G3 out of it here. So let's say G2 minus G3 is T2 minus TW over T2 minus T1 times G2 minus G1, right? Okay, so from here we'll get G3 is therefore G2 minus T2 minus TW over T2 minus T1 times G2 minus G1, right? So that's our secant method equation. All right. So I substituted this here. This is our G2. This is T2 minus T ideal over T2 minus T1 times G2 minus G1, and we get 0.6353. So our next guess, third guess, for y prime at x is equal to 0 is going to be 0.6353. Okay, so we'll resolve our differential equation. So this is our iteration number 3, and let's do xi, yi, y prime I. So x is 0, y is 1, and our guess is 0.6353. This is our guess. So we solve our differential equation, 0.25, we will get 1.1588, 0.5441. 0.50, we'll get 1.2949, 0.4530. 0.75, we do 1.4081, 0.3675. And finally 1.0, you'll get 1.5 and 0.2948. Bingo, we hit our target. So this is our solution to the differential equation. Okay, so you saw that actually secant method took only one iteration to get to our ideal guess value to match the target. Now it turns out that the equation that we had, that we were solving, y prime double prime is a function of x, y, y prime, which was x minus y plus y prime. Notice y double prime is linear with respect to both y and y prime. So when we have a linear ODE, it turns out that if we ignore round off errors, we should converge in one iteration. Of course, if we don't have a if we don't have a linear ODE, if it is a non-linear ODE, we may never match because there may be no solution, or it may take more than one iteration. Most likely it'll take more than one iteration. So linear ODEs, if we ignore round off errors, we should converge in one iteration. So let's pause also for a moment. So notice we solved a boundary value problem. How did we solve a boundary value problem? We converted into an initial value problem, which required us to make a guess to match a target. And to find our best way, we use secant method. Okay, so we have been now combining different methods that we have learned to solve newer and newer kind of problems. Let me give you an abstract picture also. So remember what we did. We have now learned about properties of a function. We have learned how to integrate a function, and we have learned how to differentiate a function. All this numerically. So when we were solving differential equation, what we did, we combined ideas of this with ideas of this. And we developed our Runge-Kutta method, Euler's method, and then we combined that with our secant method to solve a boundary value problem. Now what we can do is, to solve an ODE, we can combine these two ideas. We can take the derivative, write it in finite difference expression form, and solve a system of equations. So now in order to solve ODEs, if we combine this idea with solution of linear systems or non-linear systems, right? We learned how to solve these equations. When you combine these two ideas with this, you develop what is called a finite difference method. So when you take the next course, say in finite element or finite difference, you will find that it is basically an extension of numerical methods.